My name's Sandon Jacobs. I am a developer advocate, senior developer advocate at Confluent. And make sure I get my slides going here. A little bit about me. Personally, or professionally, excuse me, I'm a developer advocate at Confluent, like I just said 4 times. I'm a Java developer by trade. Been doing Java development for a couple of decades now. Worked in healthcare, logistics, freight rail, you name it, mobile advertising as well. Personally, I'm born and raised in North Carolina. Lived there in Raleigh, if you guys are familiar with that area, with my wife and my daughters. That's a picture of them there. Pretty much why I do the things I do. And I love to be outdoors rather than being cooped up in a air-conditioned, well, not today. It's 105 degrees, so air conditioning is a great thing for all of us. But I'm an outdoor guy, so when I'm not at the keyboard, take me fishing, take me golfing. Today, we're gonna take a little stroll down memory lane, and then that stroll is gonna take us into Apache Kafka. But as we start things out here, we're gonna look at how we built applications in Memoriam. The monolith is what we're gonna visit to start with, of course, and that'll take us into our journey with event-driven architecture. We'll talk about terminology of Kafka, build a basic understanding of the terms of Kafka from a developer standpoint, and we'll talk about some other parts of the ecosystem as well. So the title of this talk came from a story I heard about Vince Lombardi, the legendary football coach. And we're in Texas, football is religion, so we should probably have a football analogy, right? Lombardi was the coach of the Green Bay Packers, and in 1961, the previous season, they lost the NFL championship game to the Eagles. They blew a fourth quarter lead. And they had the best team there was around, and why did we blow this lead, so forth and so on. So the next year, at training camp on day 1, he decides we're going back to basics. We're going back to fundamentals. We're going to start this thing from scratch. And so he's got the best football players around, and he holds up a football in the middle of the room, and he goes, "Gentlemen, this is a football." And everybody goes, "Sure, we know that." But whatever he did must have worked, because they started the season by beating the Giants 37-0. They won 5 of the next 7 NFL championships. So I say all that to say that the fundamentals of anything are important. And so now we get to our stroll down memory lane. And when I think of the monolithic way we built applications, it reminds me of this fine American eating establishment known as the Cheesecake Factory. How many of you been there? Like it, love it, want some more of it? They've got this 38-page menu that weighs about 2.5 pounds, and you can find everything from cheesesteak fusion egg rolls to shrimp carbonara, a burger if that's what you want, salmon fillet. They do a lot of things. They don't do any of them great, but we're all just trying to get to the cheesecake, right? That reminds me of the monolith. The monolithic way of building applications did a lot of things. It serviced remote requests through REST or through RPC. It stored things in a database, maybe even 2 or 3 databases. It sent events. It sent emails. It sliced, diced, julienned. It did all the things, right? And because of that, it was complex. Because of that, testing was cumbersome. Any change you made had a blast radius, and I'm talking about a serious blast radius. I'm dating myself a little bit here. But I said all that to say that monoliths did a lot of things and did none of them extremely well, like our friends at the Cheesecake Factory. So then we decided that we needed to be a little more agile, right? Agile may be a curse word to a few of you here, but I digress. Both with our processes and with our applications, we wanted to go from the monolith to building microservices. We needed microservices that specialized. We wanted to do work in parallel streams. We wanted teams to be able to, you write the email service, I'll service these requests, I'll send the events. And we worked within these bounded contexts that we could do contract testing with. And so we built the spaghetti plot. We built the complex dependency graph of remote point-to-point integrations using REST or RPC, like I was talking about earlier, these request response couplings over these protocols. Did it really get better? Yeah, it did some. And when we were building these applications, monolithic applications, we were thinking of things. We were thinking of nouns, the state of a thing at a point in time. When we queried that thing, when we queried the database, this is the state of this train, the state of this cart, the state of this user. We didn't know how we got there, but we had the state, boy, we knew the state. But people were using our applications, that state could be changing right out from under us, right? Life is happening. Events are happening. That means there's verbs happening. Things are happening to our data. Train cars are moving. Users are changing their address. That may cause some business process to fire, or may need us to change some business processes. Items are flowing in and out of shopping carts. People are buying stuff. Now, from these events, we can start to answer more complex questions. We can start doing some deductive reasoning, some analysis, some predictive analysis on what may happen next for our business. Verbs, events. That's my dollar store version of event-driven architecture. So we're past that point in the program, and we get to talk about Kafka now. If we're going event-driven, we have some core requirements of whatever infrastructure we're going to use, right? We need high throughput, because we have to deliver data, high volumes of data, at low latencies. We need scalability to meet our production needs, scale up to meet our production needs of some of you with trillions of events per day, petabytes of data. We need permanent, durable storage. We need high availability across AZs and across geographic regions. And what we found, or that the industry has found, is that Apache Kafka ticks these boxes. The definition straight from the ASF website, it kind of spells that out, that Kafka is a distributed event streaming platform used for high performance data pipelines, streaming analytics, data integration, and mission critical applications. We could probably all stand and recite that one, right? So it's the de facto standard event streaming platform today, full stop. So let's get into the parts of Kafka itself. At the heart of Kafka is this notion of an immutable event log. It's called a topic. Topics live on servers known as brokers, and an application that wants to interface with Kafka, send data to Kafka, creates an instance of a producer to write data to that topic. Now we configure these producers to know how and where to send the events to Kafka. There's all kinds of configuration knobs that I won't go into here. Just know that there are trade-offs here when you start turning those knobs as far as your throughput and performance versus durability of your events, and you really have to make that decision for yourself based on the type of events that you're sending. For instance, if I'm just sending my syslogs to Kafka, I don't need the same guarantees as my financial transactions, because those syslogs aren't really costing anybody money, and I may not have to go to Congress for my syslogs. There are client APIs and SDKs in multiple languages like the JVM, Python, Go, .NET, JavaScript, etc. And so let's get into what events are. We see events being published from the producer and being appended to our log. And you'll notice there is a number assigned to these events. That number is known as an offset. And that offset is a monotonically increasing number that really just represents the position, the ordinal position in the log or in the topic for that specific event. So we're building a foundation of terms here as we go along. So let's talk about the terms that we've learned here on this slide. We talked about brokers, we talked about topics, the producer, and the offset. So let's keep building our notion of terms here. When a producer creates that event, an event consists of multiple parts. There are headers on an event, and these are optional for you to set. Think of headers as metadata about the event. You could stash information in the header to inform your tracing or audit logging platforms downstream, or do some kind of routing or things of that nature. We have the key. Much like in a database, the key is some identifying information about that event. And we'll talk about the importance of the key when we get into partitioning, but the key is a part of the event. That's some identifying information about what this event is. And then you have the value, the body of the event, the meat and potatoes. Here's what happened to this entity, what occurred, what just happened, and when your consumers get that event, what do they need to do with it? That informs what they'll do with it. So the terms here, key, value, headers of an event. Kafka stores events on the broker in bytes. Events are serialized using some serializer implementation that is provided through our client libraries that we just talked about. There's a lot of serializers out of the box. You can serialize as byte arrays, byte buffers, numeric types, strings, and there are also serializer implementations for industry standard libraries like Apache Avro, Google Protobuf, or JSON with schema. And so the data, when you open up a log file on a broker, you're not going to see something that you can just look at in VM and go, oh yeah, see my events, that looks great. No, it's just going to be bytes, and that's for the efficiency's sake, because these values are also compressed, or you have the ability to compress that data as you're sending it over the wire as well. So, sure, we have this immutable log. That's great. But let's talk about scaling. Let's talk about scalability, and that's where we get to the notion of a partitioned immutable log. A topic consists of one or more partitions, and producing applications actually append those events to a specific partition of a topic, not just the topic at large. So here's a topic, and this is our cart action topic that I've very creatively named here. And a producer is sending either circles, triangles, or parallelograms to this cart event. That's what my partitioner is doing. So this cart, if we get a circle, the circles are going to go to partition 0. If we get a triangle, it's going to go to partition 1. If we get a rhombus, geometry joke, parallelogram square, it's going to go to partition 2. That's just the way my partitioner is set up just for visual purposes here. There's multiple partitioner implementations in Kafka. For instance, with the Java client, this is where the key comes into play. So if you don't set the key on an event, that key is null, then Kafka by default, at least in the Java client, uses what's called sticky partitioning. So the producer is going to put together a set of events, and it's going to batch them up and send them all to the same partition. If you do provide a key, by default, the Java partitioner, for example, will take the hash code of that key for every single event and then do a modulo operation on the number of partitions for that topic, and then decide which partition that goes to. So then the events are appended to the correct partition. This is important later on when we get into consumption, because now we're looking at the order in which events are processed on a partition and ordering guarantees. So more terms here, the partition and the partitioner. And with that partitioner, there is an abstraction here where you can write your own. You can extend that to whatever you need to do in your partitioning space. So we've got a partitioned immutable log, but how do we guarantee durability? How do we get some durability guarantees out of this thing and build the distributed partitioned immutable log? I promise I won't fill up the whole screen with the title in just a minute. Remember brokers? That's where our data lives. And we have this example here with this single broker, and yeah, that's great, but we should probably have some redundancy here. Things are gonna happen. We should probably have more than one broker. And so now that we've got our brokers, let's distribute the data across the brokers. So each partition can live on a separate node, a separate broker within the cluster. Take that a step further. We need to build a distributed, partitioned, replicated immutable log so that we get the durability guarantees that we want. So we have, this topic has 3 partitions, and each topic has what's known as a replication factor, meaning how many copies of the data for a partition exist across the cluster. So as you can see here, the blue nodes here are what we call the leader partitions for that topic. Anytime a request to write or to consume from that specific partition is made from a client, it's going to come from that leader. In the background is this inter-broker communication known as replication that is happening. And that means that the data from partition 0 has been replicated to the other nodes, partition 1, partition 2 as well. So you have these yellow nodes that are replicas. More importantly, they're in-sync replicas. And what in-sync replicas mean is that at any point, if something happens to one of these nodes, that in-sync replica can become the leader, and we can carry on with our lives while we figure out how to scale the cluster back up. And that's what we're going to talk about next. What happens, not if, but when broker 2 takes a dirt nap. because it's gonna happen. It's usually gonna happen about 1:30, 2 o'clock in the morning from experience. It never happens at like 9 a.m. when everybody's done with their second cup of coffee. This is where we get the payoff from our distributed, partitioned, replicated, immutable log. So what happens here? Oh no, we've lost partition 2. We can't get this data from partition 2. Yes, we can, because broker 0 says, I've got an in-sync replica. You can come to me for that data. I'll service that. So producers and consumers start talking to broker 0 for partition 2's data, and that gives you, the operator, time to figure out how to bring broker 2 back up or spin up another broker 2. And once that happens, the cluster is going to rebalance and try to get things back to steady state. Remember, I always said when, not if this goes. Things are always going to go sideways. So that's about producing. We've got data in Kafka. That's all great. We're storing data in this, what was my title? A distributed, immutable, replicated, partitioned log. Yeah, it's all there. Now what? We got to consume this stuff. We need to ingest this data. We got to make information out of data. On the other side of these topics, we have applications that will instantiate what's known as a consumer. A consumer is configured with a corresponding deserializer for that serializer we talked about earlier to know how to ingest that data from the topic. And once it deserializes that data, then it can begin its processing, So we picked up another term here, which we haven't done in a few slides, the deserializer. And remember we talked about order of events earlier? From a partition, a single consumer is going to consume from that single partition. And it's going to consume in the order that the events were produced to that partition. So we received these offsets in this order, and that single instance of a consumer is consuming from that one partition. But what happens when we have these 3 partitions? Remember, we have our partition data here, and we've got this one consumer, and he's going to consume from partition 1 for a while. Then he's going to try to keep up and go to partition 1 for a while, and partition 2. And in a situation where you see more ingress of data than you do egress of data, you'll start noticing what's called consumer lag. And what consumer lag is the difference between the last event that the offset of the last event that the consumer actually processed, and the last event that was produced. So when you start seeing your consumer fall apart or fall behind, he's going to say this is a whole lot to handle. So we should give our consumer some help. And we can do this by instantiating more instances of a consumer. You can do this via standing up more instances of your consuming app in something like Kubernetes. You start more pods. You may just add more threads of execution to your consumer application. So now you're doing true parallel processing. And yes, that is one-to-one consumers to partitions, but what if I start that 4th guy? Well, he's going to be idle. He doesn't have any work to do because all the partitions have been assigned to someone in that consumer group. Let's go back to what a consumer group is. I skipped over that. Sorry about that. When you configure these consumers, you give them a parameter called a consumer group ID. And that configuration allows them to do what's called consumer group coordination on the broker side, meaning that the broker knows when a partition is being consumed by a member of that group. So you don't have 2 consumers colliding here and trying to consume the same exact data. So this guy, I love Mr. Bean. So this guy's just sitting around picking flowers and waiting on the next consumer group rebalance before he has any work to do. But should something happen to one of these others, the next rebalance, Mr. Bean will have to wake up and do some work, and we don't miss a beat. We keep going. If we go back and quickly revisit serialization, we talked about the different types of data that can be serialized, numeric, strings, byte arrays, and you could probably get creative here. You could say, I want structured data. I'll just put it in a string and let the consumers figure it out. Well, that raises some serious questions, especially for our consumers, when it comes to data quality and data integrity. And that's where data contracts come into play, and that's why we make mention of these standard formats like Avro and Protobuf and JSON with schema. Schema defines that data, and that schema can be shared with a schema registry of some sort. Confluent has an implementation. There's other implementations, open source ones out there as well. But this gives us some method to the madness of how that data is actually formatted in Kafka, and how it's serialized. So let's take a look. This diagram. Just imagine, if you will, we have this entity in the top left corner here called the schema creator. He's the guy who is your data architect, your data engineer, who's saying, this is what our democratized data is gonna look like, and I'm gonna define these schemas, I'm gonna register them in the registry. Your producer application uses a schema registry aware serializer implementation to say, I'm gonna look at that schema registry, grab the schema, and serialize the data to Kafka using that version of the schema. So the version goes along with the data. The consumer uses a corresponding deserializer pointed at the same schema registry. It gets that Kafka event and says, oh, this is version 0 of that cart action event. Then we go get the schema for it from the schema registry. Now I know how to deserialize it. Once I deserialize it, I can consume it. I can go on with my life and process this event, do whatever business processing I need to do. So congrats, we did it. That was it. No, joking. We have Kafka, we've got schema registry, we've got all the goodness. So we've solved the world's issues, right? No. Each and every one of you has data that is in some other system somewhere, like Salesforce or SAP or some mainframe database or somewhere else, some file system, some document management store, Mongo, you name it, that you need to do something with on top of the microservice data that you already have at your disposal. So let's work on bringing that data into Kafka so we can do our magic there. That's where Kafka Connect comes into play. We're going to talk about some other parts of the Kafka ecosystem here. Kafka Connect is a tool for scalably and reliably streaming data between Kafka and an external system. If that's a source system, then what we're basically doing is grabbing that data from that system and using a producer to produce it into Kafka. Kafka Connect is built on top of the producer and consumer that we've been talking about so far. Sync works the other direction in that your Kafka connector is going to consume data from a Kafka topic and write it to some external system. Kafka Connect provides you with a framework for writing your own connectors. There are hundreds of connectors already in the open source universe and some paid connectors as well. But there's an API, a client API to write your own. There's REST interface for submitting and managing the configuration of those connectors. It's distributed and scalable by default. And this really allows us to bridge this gap between streaming and batch applications, because a lot of these logos that you see here may not all be streaming by nature. But once we get the data into Kafka, we can start acting as if all this data was streaming. If there's data from these other systems that's coming into Kafka, it's coming from our microservices, we do need to process that data. This is where we start talking about stream processing, and you're going to hear terms all week. You're going to hear Kafka streams. You're going to hear a lot about Flink here. But really what the notion of any of those is, if we go back to our noun-verb analogy, is this notion of, are we actively querying passive data, or are we passively querying active data? Now, I know it's early and you just came out of the keynote and I might have lost you there. If we're talking about actively querying passive data, that is our traditional way of doing things, where we run a query, we do some joins, we do some aggregations, and our DBA is like, what in the heck are you doing? Why does this bleeping Java app have all my job threads consumed? If we operate on that data as it happens, as the events come in, we can reshape and read optimize that data for our read use cases and store it in that read optimized format, so that when our applications come to consume that data or come to query that data, there's not any of this transformation and massaging that needs to happen. For the Java community, there's an option for this is Kafka Streams, which is a part of the larger Kafka ecosystem. Kafka Streams is a client library for building applications and microservices where the input and output are Kafka. So you take input from one or more Kafka streams, Kafka topics. You can perform operations like transformations, filtering, routing, aggregations, time-windowed operations, joins. And then you produce that result to another Kafka topic. Yes, another Kafka topic. But you're also in the throes of building a data streaming pipeline here, right? So if you write that data to that other Kafka topic and it's bound for SAP later on, excuse me, that's where Kafka Connect comes into play that we just talked about. Now I got that read-optimized data, I'll write it to that external source system. And there are other players in this space. You're gonna see squirrels everywhere. There's Slink. I'm dating myself with this slide a little bit with Apache Storm. That was kind of my first foray into stream processing many, many years ago. Spark Streaming, I think Samza is around in some way, shape, or form still. Alpaca, for those of you in the Akka community. And what was the name of that one that I just put on there? That's a Python project, and I should have put the name of it in my slides, and I do apologize. But I do encourage you to look at all these because each one of them has their own strengths and weaknesses, and you've likely made an investment already in some platform like Spring for you Java folks, or maybe Spark for a lot of the Spark folks in the house here. Bake off, experiment, compare, contrast what meets your needs. And with that, you'll see my socials on here if you're interested in reaching out to me. Yeah.